Alright, let's talk about positron emission. Alright, so positron emission means that now you're going to be producing a positron. And just so that I remind you of it, the positron is the antiparticle of the electron. Specifically, it has a +1 charge as opposed to a -1 charge. In every other form, the positron is actually identical to the electron. It's just that the charge is different. It's the opposite of the electron. So we're going to have this positron with a +1 charge, which basically means that, oh yeah, and by the way, whereas in beta emission, where you were producing the electron, and in addition you produce the antineutrino, for positron emission, which is the antiparticle of the electron, you will produce the antiparticle of the antineutrino, which will be the neutrino itself. But because the charge of the positron is positive, that means that the atomic number of the new element is going to be one less than what it used to be, right? Because C minus 1 plus 1 will have to equal Z. The atomic mass, however, will remain the same, since the positron, much like the electron, don't have any charges. They don't have any charges yet. So what's going to happen now is that we're going to reduce the atomic number by 1 unit. So let's do a few examples of that. Let's say we have argon-33 undergoing positron emission. So we have the positron and we have the neutrino. Okay, now we find out what's going on with the element here. If the mass was 18 to begin with, that means that the new atomic, if the atomic number was 18, that means that the new atomic number will be 17. The mass, however, the mass number will remain constant. So if we look at the table, we're basically shifting from argon to chlorine. So the element in question here is chlorine-33. Similarly, if we start with germanium-64 and we undergo positron emission along with the neutrino, the mass number will go down by 1 unit, so now it's 31, and the atomic number will now be 31. The mass number will remain as 64. And looking at the table, we're basically going from germanium to gallium, so the new element is gallium-64. Alright, another one, niobium-87, undergoing positron emission. The atomic number will go down by 1 unit, so will now be 40. The mass number will remain the same. Looking at the table, element 40 is zirconium. So we will actually input zirconium as the symbol for the element. And lastly, europium-139, undergoing positron emission. The mass number will go down by 1 unit. The atomic number, will go down by 1 unit. The atomic mass will stay the same. Now, element 62 in the table is none other than samarium. So we just import the symbol for samarium right here. And like that, you basically have your positron emission balanced. So just to recap, beta emission, you're producing an electron along with the antineutrino. Positron emission, you're producing a positron along with a neutrino. Alright, so now let's take a look at electron capture. Here, this is probably the only reaction out of the 4 simple ones where you will actually have an additional reactant present, specifically an electron. Because as the name implies, in the course of this reaction, you will actually take up an electron to complete the nuclear reaction. So the electron is now a reactant. And what that means is that you're going to be producing a neutrino on the other end. You will also have to lower the atomic mass because Z minus 1 has to equal Z minus 1. And the atomic mass, however, will remain constant. So much like positron emission, we're going to be reducing the atomic number by 1 unit. So let's do a few examples. We have rubidium-76. If this undergoes electron capture, the mass number, as you can see here, will have to go down to 36, right? We also have the neutrino being produced. 36, the mass number will remain constant. So looking at the table, element 36 is none other than krypton. So we input that in here. Alright, now another example. Germanium-64 undergoing electron capture. The mass number will go down by 1 unit. The atomic number will go down by 1 unit, and the mass number will remain constant. So what this means is that we're dealing once again with gallium in this particular example. Also, don't forget you have a neutrino being produced in the process. Alright, molybdenum-90, electron capture once again. All right, we'll produce the neutrino. The atomic number will go down by 1 unit, so now it will be 41. The mass number will stay constant as 90. And element 41 is actually niobium. So now we're producing niobium 90 in the process of electron capture. Finally, erbium. Erbium 146. Undergoing electron capture will produce the neutrino, but the atomic number will go down by 1 unit. It will now be 67. The atomic mass will be 146. And looking at the table, element 67 is holmium. All right, so we'll input that as the identity of the element. All right, so this is pretty much it for electron capture. Now, fission and fusion are typically the reactions that involved in nuclear processes in nuclear reactors. Fission in particular characterizes itself by starting with an isotope of an element, usually an isotope that is high in atomic number and high in atomic mass. And this isotope usually gets activated by having a neutron added to it. And in the process of that neutron absorption, you pretty much break apart the nucleus into two halves. So you produce a bunch of neutrons in the process. So this is kind of like a self-cascade that fits itself the moment the reaction starts. But you produce not just one product isotope, you produce usually two. So let's say that the atomic number for the first one is Z sub 1. What that means is that the atomic number for the second one will have to be Z minus Z sub 1 in order for everything to add up to Z itself. The atomic mass, if the atomic mass for the first isotope is A sub 1, since we have A plus 1 on the reactant side and we have a number of neutrons with a mass number of 1, the mass number for the missing isotope will have to be A plus 1 minus A sub 1 minus 1 times A. Right? So we will actually have to multiply the balancing coefficient in front of your particle by the numbers in order to balance this correctly. So I'm going to show you a couple of examples to make it clear. But you do produce isotopes that are smaller from the bigger one. All right, so here we go. We have uranium-235, absorbing a neutron. And in the process, we are forming 3 neutrons and cesium-143. Now we need to find out the missing particle. All right, so looking at the atomic numbers, 92 plus 0 is just 92. 55 plus 3 times 0 is still 55. So all we need to do is subtract 55 from 92, and we find out that the atomic number is 37 for the missing particle. Okay, for the atomic masses, it's a little bit more complex. We have to add 235 plus 1, that will be 236. 236 minus 143 will equal, I believe, 93. And then you have 3 neutrons multiplied by 1, so 93 plus 3 should be 96. Let's see if I got that correctly. Oh, a little off. Okay, so 90. Yes, I would recommend maybe doing that with your calculator, because as you saw, even I doing it by, with my head only, I even then got it incorrect. But just to recap, we add 235 plus 1, we subtract from that 143, and from that we subtract 3 times 1, and that should give you 90. Now, element 37, if you look in the table, is actually rubidium. So you just have to input the symbol for rubidium to complete the process. And similarly, if we have plutonium-239 absorbing a neutron, this is producing barium-137 along with 15 neutrons. So now we need to find out the missing particle. Okay, so 94 plus 0 is 94. 94 minus 56 and minus 0 is 38. You might want to do that with your calculator just to be sure not to mess it up. And for the mass number, 239 plus 1 is 240. 240 minus 137 will give you a number. That number needs to be subtracted not by 1, but rather by 15 times 1. So the number you should get here will be 88. And I recommend you do that with your calculator just to avoid making mistakes. Now, element 38 is actually strontium. So we will just input the symbol as SR for the missing particle. Let's do a few more examples. Uranium-235 acquiring 1 neutron, but this time around we're producing strontium-90 along with 2 neutrons. Alright, so the missing particle first with atomic numbers, 92 plus 0 is 92. 92 minus 38 will be roughly 54. And 54 minus 2 times 0 is still be 54. Alright, now 235 plus 1 is 236. 236 minus 90 ought to be 146. 146 plus 2 times 1 should be 148. Let's see if I got that right. Oh, you see? I keep messing it up. So use a calculator for the atomic masses. I'm trying, but I can. This morning it's not working for me. All right, now element 54 is xenon. So you just need to input the symbol for xenon now that you know the atomic number. And for the last example here, what I'm doing, you might say is that, well, this is already balanced, except that if you look carefully, you realize, oh, the balancing number for the neutrons hasn't been accounted for yet. So what we need to do is add all the values together. Now the atomic numbers are not going to help you in any way, shape, and form because the neutrons are always going to be 0 for the atomic number. So that's already balanced, right? 93 is equal to 36 plus 57. That you can use to confirm that everything else is accounted for. But to determine the number of neutrons, you have to look at the mass numbers. 239 plus 1 will be 240. Let's see. 240 minus 150 is 90. 90 minus 84 is 6. Since the mass number of the neutrons is 1, what that means is that to come up with a 6 difference between these numbers, you need to multiply the number of neutrons by 6. And see if I got this right. This time around I did get it right. Alright, so just be aware of that. Different things that I could ask you about, right? It might not necessarily be the number of isotopes, but rather the number, or excuse me, the identity of the isotope in question, but maybe the number of neutrons that you're producing. Alright, the last equation we're going to talk about is fusion. Now fusion is in some ways the opposite of fission. Here you have two different isotopes of relatively smaller mass, smaller weight, and smaller atomic numbers combining together to give you an isotope of higher mass and higher atomic number. So you combine smaller nuclei to make bigger ones. So an example of that would be taking two protons together and combining them to make hydrogen 2. In this case, the mass numbers are balanced. 1 plus 1 equals 2. But 1 plus 1 does not equal 1 for the atomic numbers. So that means that we're missing one particle, which has to have an atomic number of 1, but the masses are already accounted for, so the mass has to be 0. And so what this will tell you is that the missing particle, there's only one particle that contains this type of feature where the charge is plus 1 and the mass is 0. And that is the positron. So this is the positron you're dealing with, which technically, means that you also have to have a neutrino. Okay, what about if you take helium-3 and combine it with helium-4? If I only give you, like a gamma ray that's being produced, what I'm implying is that you're making just one isotope. So you just have to add up numbers together. 2 plus 2 will give you 4. 3 plus 4 will give you 7. So if you look at the table, look for element 4, you'll realize that that's beryllium. So technically what you formed right here was beryllium-7. Alright, here goes another example. Let's say that we start with helium-3 and we're producing 2 helium-4s and 1 proton. Okay, so now we're missing the reactant particle right here. So let's find out what that reactant particle is going to be. If we look at the atomic numbers first, okay, we have 2 for helium-3, but for helium-4 we have 2 times 2, so it's actually 4 on the on the bottom portion of the isotope. So 4 plus 1, that's 5. 5 minus 2 is 3, so the missing number right here will have to be 3. Now for the atomic masses, you have 3 for helium. On the product side, you have 2 times 4, which is 8. 8 plus 1, which is 9. 9 minus 3 tells you that you're missing a 6. And if you look at the table, element 3 is actually lithium. So you're dealing with lithium-6 in this process. Alright, one more. Oxygen. You're burning oxygen-16. And in this process, you're forming 2 helium-4s. So we're going to do the same thing. For the missing element, let's take a look at the atomic numbers. 2 times 8 is 16. 2 times 2 is 4. 16 minus 4 is 12. So that's the number for the missing isotope. 2 times 16 is 32. 2 times 4 is 8. 32 minus 8 gives you 24. So that's the mass number of the isotope missing. And if you look at the periodic table, you'll look and realize that magnesium is element 12. So you just input that as the isotope mass. All right, and with all that being said, we finish all the examples for fission and fusion in this particular video. In the next one, I'll just give you my final thoughts about nuclear chemistry. So see you then.